Look up at Mars tonight, shining like a brilliant orange star in the darkness. At its closest approach to Earth, it appears at magnitude -2.94, one of the brightest objects in our night sky. But how much light is actually reaching your eyes? The answer might surprise you. Just 0.00004 lux. To put that in perspective, that's roughly 25,000 times dimmer than a candle viewed from 1 meter away. Let's quickly have a look at how we get this low value for Mars. We can use Mars's stated apparent magnitude, how bright it is. Using the formula at the top, we get 0.0000398 lux for Mars illuminance on Earth and your eyes. You can easily check this yourself. Go on any AI and ask, calculate the lux arriving on Earth from Mars at apparent magnitude -2.94. Ask it to show the calculations and references. This is our starting point. Mars as we see it with the naked eye, delivering 0.00004 lux to our retina. But here's something crucial to understand. Unlike stars, which appear as point sources of light, Mars has a measurable angular size. It's what astronomers call an extended source. Even to the naked eye, Mars isn't truly a point of light, but a tiny disk with actual width and height in the sky. This distinction is fundamental to understanding what happens when we magnify it through a telescope. When we magnify an extended source like Mars, we're stretching that tiny disk larger while spreading the same amount of light over a bigger apparent area. This is the key to understanding the brightness magnification trade-off we're about to explore. Our setup is straightforward. A 150mm telescope observing Mars at its closest approach when it shines at magnitude -2.94. To help visualize what the eye sees through different magnifications, we've placed boards at a distance of 10 meters, each size to match Mars's apparent diameter at various magnification powers. Let's start with the magic number, 21.42 times magnification. This isn't arbitrary, it's calculated by dividing our telescope's aperture by the human eye's pupil size of 7 millimeters. It's a simple calculation. It's the square root of the light-gathering power of a 150mm scope, based on a 7mm diameter pupil. At this magnification, Mars appears larger than to the naked eye, but maintains exactly the same surface brightness 0.00004 lux, not accounting for loss of light from the optics. This is our equal brightness zoom, the theoretical sweet spot where we maximize size without sacrificing brightness. But what happens when we push beyond this optimal point? At 50 times magnification, Mars grows to 60.6 millimeters on our demonstration board, but its surface brightness drops to just 0.000007 lux, only 18% as bright as the naked eye view. Double the magnification to 100 times, and Mars expands to 121 millimeters, but brightness plummets to 0.000018 lux, just 5% of naked eye brightness. At 200 times, our demonstration board shows Mars at 242 millimeters diameter. Surface brightness has dropped to a mere 0.00000046 lux. It's around 1% of naked eye brightness. This is often considered the practical upper limit for planetary observation. This demonstrates a fundamental law of optics. When you magnify an extended object like a planet, you're spreading the same amount of collected light over a larger apparent area. More magnification means less light per unit area reaching your eye. For just seeing Mars's color at 200 times magnification, you can use a much smaller telescope. Even a 3-inch 75mm telescope will easily show Mars's distinctive red-orange color at 200 times. The color is actually one of the easiest things to observe about Mars. At 200 times magnification with a 3-inch scope, the trade-off is the visible light hitting your eye is approximately 50% less than with a 150mm scope. Mars will appear as a small but clearly colored orange-red disk. The color will be much more obvious than with naked eye viewing. You won't see surface details, but the color will be unmistakable. This now brings into question, from an extended light source, are our eyes capable of perceiving color at such a low level? The generally accepted level to perceive red-orange is 0.02 lux, sensitivity peaking at around 590 to 600 nanometers. Yet in this study, titled The Color of Night, conducted in a lab, they got a minimum level of 0.0032 lux. If this is the minimum to perceive red-orange in a lab, then given the amount of light at 200 times magnification, it would be impossible to perceive Mars's color. This now brings into question the actual brightness of Mars. It must inevitably be a lot brighter than we're told. According to every astronomy textbook, Mars at its brightest has an apparent magnitude of -2.94. Using standard photometric conversions, this translates to about 0.00004 lux of illumination. Now, your 150mm telescope gathers about 459 times more light than your dark adapted eye. So far, so good. But at 200 times magnification, that light gets spread over an area 40,000 times larger than the original image. Run the numbers: 0.00004 lux times 459 for light gathering divided by 40,000 for magnification. The result? Around 0.000000046 lux, hitting your retina. Here's the problem. According to color vision research, specifically studies on the minimum light levels needed to perceive color, you need at least 0.0032 lux to see red or orange. That's the absolute minimum threshold established in laboratory conditions. But we calculated 0.0000005 lux. That's about 6,000 times less light than needed for color vision. Yet there you are, clearly seeing Mars as red-orange. Not just you, thousands of amateur astronomers around the world, every clear night for over a century. All seeing the same thing. All seeing color where, mathematically, color should be impossible. So, what's going on? Let's systematically eliminate every possible explanation. Magnitude to lux conversions. Could our brightness calculations be wrong? No. Multiple independent methods all give the same result. Whether using standard photometric conversions or the inverse square law, every approach converges on the same values. The conversion methods are rock solid. Light gathering calculations. Could we be wrong about how much light the telescope collects? No. The light gathering power of a telescope is simply the ratio of aperture areas. A 150mm telescope versus a 7mm pupil gives exactly 459 times more light. Basic geometry. Magnification effects. Could we be miscalculating how magnification spreads the light? No, when you magnify an image 200 times, the light spreads over 200 squared or 40,000 times the area. This is fundamental optics, understood for centuries. Could the dark background somehow add light? No. Contrast can make existing photons more detectable, but it cannot create photons that aren't there. Physics doesn't work that way. Visual system anomalies. Could there be something special about how our eyes work with concentrated light? No, at 200 times magnification, it's an extended source. The 0.0032 lux threshold for color vision is well established across multiple studies. Our visual system can't magically see color with 6,000 times less light than required. Measurement errors. Could there be systematic errors in how planetary magnitudes are measured? No, these values have been consistent across decades of independent observations using different instruments and methods. Mars has been measured as magnitude minus 2.94 countless times. We're left with only one logical conclusion. Mars must be significantly brighter than published astronomical data suggests. Not just a little brighter, thousands of times brighter. But here's where this gets truly profound. If Mars's brightness is wrong by this magnitude, then every planet's brightness is likely wrong by similar factors. Why? Because they're all measured using the same photometric methods, the same instruments, the same conversion standards. This isn't just about Mars. This suggests a fundamental error in planetary photometry that has persisted throughout astronomical literature for decades. All the planets are potentially orders of magnitude brighter than we've been told. The evidence has been staring us in the face every clear night. Every time an amateur astronomer looks through a telescope and sees the colours of the planets, they're witnessing proof that our fundamental measurements are wrong. Sometimes, the most profound discoveries come not from exotic experiments, but from simply paying attention to what we can see with our own eyes. and asking why the math doesn't match reality. The fact is, seeing the colour of Mars through a telescope destroys the heliocentric model. Our next video will be experiments that you can do to prove Mars must be brighter.